Talk number one, the current mysteries in physics. So the first mystery in physics gives me a great excuse to show an amazing photo of a galaxy. So the mystery is sort of known as dark matter, and dark matter is kind of the term for the possible explanation, but it's also just the term used for the problem itself. So the problem is galaxies spin. They're usually reasonably flat. This is almost like a top-down view of one. So galaxies sort of spin generally on a plane, and if you do the calculation based on the number of stars that you can see in the galaxy, and based on how bright those stars are and the frequencies of light they're given out, you can work out what type of star they are, how big they are, and therefore you can work out how much mass should be in this galaxy. And if you do that, you can work out from the amount of mass how much gravity there should be pulling the galaxy together, which then tells you how fast it should be able to spin without just flying apart. And the answer is nowhere near as fast as it's spinning. And this is the case for pretty much all galaxies. They all just spin way, way, way too fast for the amount of gravity that should be there to be able to hold them together. So they should just be ripping themselves to pieces and flying off into space. And for some reason, they're not. And so dark matter is this proposed extra bunch of matter, which is just somehow sitting in among the stars, providing extra mass and therefore extra gravity to hold the whole thing together. Now, nobody's ever seen dark matter, partly because it's dark, but possibly because it doesn't exist. There are various theories about what it could be, how it might sort of induce its extra gravity among the matter around it, but nobody's really come up with a good explanation. And all of the explanations that exist all then contradict some other part of physics. So nobody's managed to come up with a sort of plausible type or explanation of dark matter that doesn't then break something else. To give you an idea of like how big this problem is, or how effective dark matter would have to be, if you were to do the calculations on how much dark matter there is compared to normal matter, it's something like a ratio of 4 to 1 of like dark matter to real matter. So this is a big problem. Personally, I think that the more likely explanation is that our theory of gravity just doesn't work at large scales. That the theory of gravity we have is great for like dropping a brick off a building and doing the calculations for that, or it works for kind of the Earth going around the sun, but it doesn't work for the sun going around something that's orders of magnitude bigger. So I think it will turn out to not be a thing, but there are many, many physicists who believe that it is a thing. We just can't see it or feel it or touch it. We can only see it happening in galaxies far away. So that's problem number one. Problem number two gives me another great excuse to show an amazing picture of space, which is not a picture of stars, it's a picture of galaxies, which blows my mind. So the second problem is that all of the galaxies are moving away from each other at an ever increasing speed. So it would kind of make sense if the Big Bang had blown stuff up and everything was just flying apart. The problem is that everything's flying apart at an ever increasing speed. And that means there must be energy being added in order to give it that acceleration. So somewhere there was like someone with a bike pump adding extra energy into the universe to push all these galaxies away from each other at an increasing pace. This has a few like interesting sort of connotations. One of them being that because the galaxies are moving faster and faster away from each other, some of them are now moving away from us at more than the speed of light, which doesn't quite make sense because you think nothing can travel that fast. But if you look at it from the perspective of it is actually space expanding, then it is kind of plausible. It also means that there are galaxies, therefore, that even if we build a spaceship that can go at the speed of light, we will never be able to get to those galaxies because they're now moving away from us at more than the speed of light. So there are bits of the universe we will never be able to get to, and possibly bits of the universe that have already disappeared that we will never be able to see because they've already gone more than light speed away from us. There could be like almost a whole other universe out there that's just in the past and has disappeared too far away, too fast for us to get to. The amount of supposed dark energy that would be needed, if you equate energy to mass, which we'll get onto at some point, then the amount of equivalent dark energy compared to the amount of matter in the universe is something like a ratio of, I think it's like dark energy would be about 85% of the universe. Dark matter would be about 10%. I've definitely got these numbers wrong. And real matter would be something like 5%. I forget the real numbers, but essentially you'd need a huge amount of dark energy in order to make things accelerate the way they are. My favorite alternative explanation for this is that actually we're all shrinking, which I think is brilliant. It would require that we are shrinking at quite a pace. But if you think that we are shrinking, all of our atoms are shrinking, and all of the galaxies are shrinking, then it looks like we're moving away from each other, but we're not. So the next general mystery in physics is that photons are really weird. They behave in strange ways, which sort of make no sense. Quick recap from school. Photons are any part of the electromagnetic spectrum. So radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays are all just photons of the electromagnetic spectrum. I might occasionally interchangeably use the term light and photons because they're sort of the same thing. Light is just a specific frequency of photon. One key thing about photons, which will become important later, is that the energy of a photon is directly proportional to its frequency. So gamma rays, which have a very high frequency, have a very high amount of energy per photon. And radio waves at the other end of the spectrum with a very low frequency have a very low amount of energy per photon. So photons are just these packets of electromagnetic energy. And we know that they are discrete packets of energy because of an experiment. The experiment is called the photoelectric effect, and it basically involves shining light onto a lump of metal. So you see on the left coming in, we have photons, wiggly lines. The photons are hitting the metal and are ejecting electrons, which are in red. So have I got another slide for this? Yeah, I have. So when you do this experiment, you shine light onto a piece of metal, electrons fly out. And it doesn't matter whether you have a huge light bulb making it really, really bright or a really, really dim light bulb. It makes no difference to whether or not electrons are ejected. And it makes no difference to the speed at which the electrons fly out. The only thing that makes a difference to whether or not electrons are released is the frequency of the light. So essentially, if you take a single frequency of light, say like a particular shade of red, and you shine that frequency of photons on a particular type of metal, you may or may not get electrons emitted. You can turn that bulb up as bright as you want, and the electrons coming out will come out at the same speed. You just get more of them coming out. And essentially, you can adjust the brightness or you can shine it for a different length of time. It doesn't affect the speed of the electrons. But if you reduce the frequency of that light, then eventually electrons will stop being released. So this kind of shows that each photon is a discrete packet of energy because each photon either does or doesn't have enough energy to release an electron. This was kind of I think a discovery of Einstein. He didn't necessarily do the experiment, but he theorized that the experiment showed that photons are individual packets of energy. They are not continuous waves. So knowing that, we can now look at another behavior of photons, which shows the opposite. This is the famous double slit experiment, which involves shining light through two tiny slits in a screen. Before we do that, we've got a slide with some really badly organized animations on it showing wave interference. Wave interference applies to any types of waves, waves in the sea, sound waves, sort of waves of voltage in a wire. The theory is the same. So if you sort of add two waves together, they will combine and will either sort of cancel each other out or will amplify each other or something more complicated. So on the left, we've got two waves, and you can see they are the same frequency and their peaks and their troughs perfectly align on top of each other, which means that when those two waves combine with each other, you get a single wave, which is double the amplitude. Similarly, if those waves are out of phase with each other, like this, so you've got the peaks and the troughs are going in opposite directions, then when they combine, you just get nothing. So with that in mind, we can now shine some light through a couple of slits and then see what happens to that light when it hits a screen behind the slits. Something like this. So on the left, that orange dot is emitting light. The single slit is not particularly important. What's important is the slits marked A and B. So all the photons travel either through slit A or slit B, and because they are waves, they then combine with each other and interfere, and they then eventually hit a screen on the right. And what happens on that screen is that due to the different ways that those waves combine, you get sort of peaks and troughs of brightness on the screen, something like this. So I really struggled to find a diagram that sort of explained this well, but essentially, as the waves of photons traveling through one slit interfere with waves traveling through the other slit, depending on where that happens on the screen, the waves will be in different phases, and you'll get these sort of patterns of brightness and darkness on the screen that they hit. If you were to look at that screen face on, you end up with something like this. So you can sort of see those. I mean, obviously everything sort of gets less bright as it goes out to the side because fewer and fewer photons scatter that far. But in the middle, you've still got this pattern of lightness and darkness as those different photons are interfering with each other. But what's weird is that if you only fire one photon at a time, it still interferes with itself. So you still get wave interference when one photon goes through at a time, which suggests that that one photon is going through both slots simultaneously and interfering with itself to give you exactly the same pattern building up on the screen behind. So photons behave both as particles and as waves and as just totally weird things that can be in two places at once. To make it even more strange, you can do the same with electrons. You can do the same with neutrons. If you fire electrons through two slits, one at a time, they will also interfere with each other and create a pattern of peaks and troughs on the screen behind. So photons and matter appear to be able to go in two directions at once. This experiment also gets weirder when you try to put detectors on the slots to see which slit something is going through. And essentially, things appear to go through both slits at once until you observe them, and then they stop doing it, which gets into all kinds of philosophical debates about whether the universe is in every possible state at the same time until consciousness observes it, and that therefore consciousness is what causes the universe to manifest itself. But trying to stick to physics instead of philosophy, that is a brief summary of the total weirdness of photons and the dual slit experiment. The other weird thing about light is that it doesn't travel in straight lines, which is what we were all told in school. So you probably remember something a little bit like this from school. You have something emitting light over on the left, you have a mirror, and then you can detect that light on the right. And as is written at the bottom, the angle of incidence equals the angle of reflection. So light will not, if you take the mirror away, you will get no photons at the detector because the light cannot just bend itself around the barrier. So light travels in straight lines, and light reflects with an equal angle coming in as the angle going out. This is what we were all told in school. We were lied to. So it appears that what actually happens, if you start to dig into it, is that light travels through every possible path that it can at the same time, but that paths which are equal in distance but opposite to each other cancel each other out, leaving only the straight path uncancelled. So to try and explain this, what actually happens is that a single photon from the photon emitter on the left hits the mirror all the way along the mirror, but that if you look at the furthest left path that sort of comes straight down from the emitter to the furthest left point on the mirror, and then bounces up on a long line to the detector on the right, there's a sort of equal and opposite path of that, which goes from the emitter on the left on the long gradual path to the far right, and then up to the detector. And those two paths of light appear to cancel each other out. So every equal and opposite path cancels, which leaves you with just that straight line path in the middle. How do we know this happens? Well, you can start to play around with the mirror, and you can prove that light is not just traveling through the straight path in the middle. If you do this, you get, sort of unsurprisingly, nothing at the photon detector. If you take away the piece of the mirror that you would expect to be reflecting that straight line path, you never get any photons at the detector. But weirdly, if you do this, you also get nothing at the detector. You cannot simply leave the middle part of the mirror and get a reflection. You actually need some length of mirror for the photons to be reflected. But then it gets more weird when you do stuff like this, where the middle of the mirror is missing, but you've got some other odd bits of the mirror instead, and then you do get photons detected at the detector. And I mean, this is sort of simplified in that I've only got 4 pieces of mirror, but you would in reality do this with a mirror with probably sort of hundreds of thousands of very closely divided bits of mirror. And if you scratch out the mirror in the right way, which has to be done specifically for the frequency of light and for the sort of distances involved in terms of geometry, then you can make reflections with bits of mirror missing, and it works. So it appears that light travels through every possible path at the same time, and then cancels itself out in every way except the way that's in the middle, because that doesn't have an equal and opposite path to be cancelled. So in summary, light is totally nuts, goes through every possible path at the same time, goes through multiple slits at the same time, but it's a particle and it's a wave. Totally straightforward. So that sort of concludes things in physics, which I think are the most important things which physicists know are crazy. But I think there are also some things which physicists don't necessarily think are crazy, but I think are a bit suspect. The first one is to do with Einstein's theory of special relativity, which in its simplest form just says that everything is relative. For example, if you are just floating through space and something else is floating through space, are they moving or are you moving? Einstein's theory of relativity says, well, it's just relative. So if you and me are moving towards each other in space, I could say that you were moving towards me. You could say that I'm moving towards you. And according to Einstein, both of those positions or those frames of reference are equally valid. Another thing that Einstein's theory of relativity says is that the faster you travel, the slower time happens for you from the perspective of someone else. So again, it's kind of relative. So when Usain Bolt travels really, really fast, when he finishes his race, for him, it happened at a normal speed. But for us, his time was running slower. So when he finishes his race, he looks slightly younger than he should do. Difficult to tell, even at Usain Bolt speed, but you can see he does look pretty young. And that is because relative to how fast time goes for us, his time is going slower because he's traveling faster. Now, this gives rise to an interesting problem known as the twins paradox. And the twins paradox says this. As you can see at the top, there's a very, very large person standing on the Earth, and his twin sister goes off on an unconventional space rocket where you sit on the outside and goes off to visit a nearby star. She is traveling at some colossal speed, and therefore time goes slower for her. She comes back from her trip to the nearby star, which may have taken her, according to the clock on this, 5 minutes, probably more in reality like 5 years. But when she gets back on Earth, a lot more time has passed because she was traveling quickly. So she gets back and like, hey, how are you doing? That was a good 5 years. Her twin brother is like, what do you mean 5 years? That took you 70. So the faster you travel, the slower time goes according to somebody else's perspective. She won't have noticed that her time was going slower. Her watch and her clock in the spaceship will all look completely normal. Time will just appear absolutely as normal for her. Paint will dry at the same slow speed, etc. But for somebody on Earth, what seemed to her like 5 years might seem like 70 on Earth. But there's one problem with this theory, or one problem with this situation, which is that if every position in space is relative, then it's perfectly valid for her to argue that she never moved at all. She sat on her spaceship, the Earth moved away from her, and then the Earth moved back towards her, and she stayed still, and it was Earth that moved. And therefore, she should be the older one, and it's her twin brother who should look younger. So everything is relative, apart from it's not. And I think I'm pretty sure experiments have been done to show that. I don't think we've actually sent someone's twin to a star, but we have like sent atomic clocks around in airplanes. And it does appear that the person who takes the journey does end up being younger, or the atomic clock ends up being slightly behind. But I sort of encourage you to go and look at videos of this on YouTube and to try to get an explanation for it. And there are explanations, and some of the explanations are like, yes, well, all of the positions are equally valid, but she was the person who accelerated, so it's her who's younger. But Einstein's theory of relativity doesn't say anything about acceleration as such, so that argument's sort of invalid. And if you look up some other explanations, that try to explain this, they actually say, no, the acceleration argument is not valid. Here's this other explanation involving some complicated diagrams involving time and space, and then we turn those diagrams through weird angles to reflect different people's perspectives of time. And I think they all somewhere trip themselves up or trick themselves into an explanation, and I don't think it's correct. And in a later talk, I'll go into an explanation of why time slows down when you travel through space, and we'll see that actually there is an explanation for this, but that the current ones aren't really valid. So this is the famous Schrodinger's cat thing. And I'll talk just a little bit about where the idea of Schrodinger's cat came from, and the fact that even Schrodinger thought it was weird. So this comes from the idea of things being in every place at once. As we saw with photons, they appear to be able to be in multiple places at once. And we also saw with the double slit experiment, you can fire electrons one at a time, and they appear to go through two slits at once. So this is the idea of superposition, meaning that something can be in the sort of superset of positions. It can be in all of the possible positions at once. So you may remember this diagram of an atom from school. You have the electrons flying around the outside and the nucleus in the middle. But what physicists tend to actually think of this as is something more like this. Now, this is the probability cloud for the electron, which says we don't actually know where those electrons are until we observe them, and therefore the electron is actually in every one of those positions at the same time, just with a varying level of probability. So we just have this sort of probability cloud where the more orange bits are the more likely locations for the electron, and the more yellow bits, the less likely locations, but really it's in every one of those locations at the same time until we look at it. So in discussion about this, Schrodinger came up with a sort of consequential hypothetical situation, which you probably all know about. It involves a cat and some poison and a single radioactive particle sat in a box. So when that single radioactive particle decays, it will, in this diagram, do something to a hammer on a piece of string, which will then release the poison and the cat will die. And radioactive decay is entirely random. Again, it has a probability, but you never know when a particular radioactive particle is going to decay. So you have no idea whether or not that particle has decayed. You have no idea whether the poison has released, and therefore you don't know whether or not the cat is dead or alive. And Schrodinger said, well, going on this idea of superposition, that things take on every possible state that they can until you observe them, that means that the cat is both dead and alive at the same time. And Schrodinger knew, just as we did, that that's not how cats work, because catties are not dead and alive at the same time. So he actually proposed this idea to show that he thought the theory was wrong. Schrodinger's cat is often sort of taken as this idea, as if it was Schrodinger's idea that things can be in multiple states at the same time. But he was actually using this hypothetical thought experiment to try to show that he thought the theory was ridiculous. Obviously, the theory is ridiculous because, as we all know, a cat will only go in a box that it perfectly fits into, and therefore you're never going to get the poison in as well. The next piece of weirdness that doesn't quite make sense is the idea that time slows down when you travel at speed. Have I got a picture for this? No, this is just me talking. So this idea in special relativity that as Usain Bolt runs faster, or as your twin in their spaceship travels faster, that time slows down for them as you observe it. The odd thing about this, though, is that nobody's ever said why. And I think it's interesting, especially with some of Einstein's stuff, that there's almost a kind of Einstein said so, and we've done an experiment and we've tested it and it's true, therefore it's fine, we'll carry on. But there is no explanation as to why time slows down. There are sort of these ideas that space is actually a four-dimensional thing, where you've got three physical dimensions and a fourth dimension of time, therefore it's space-time, and the faster you move through space, the slower you move through time. But there's still no explanation as to why or how. Again, I would encourage you to either go and watch some YouTube videos about this or just do some thinking about it. And I will come back to this in a later talk. But I think that this is suspect, that we just have this edict from Einstein that time slows down, which it very much appears to do, but there's no explanation as to physically how or why. So that concludes the main points of weirdness in physics. Quick summary: galaxies go too fast, so there should be some kind of dark matter. Galaxies are accelerating away from each other, so either there's some kind of dark energy pushing them apart, or everybody is shrinking. Photons are both particles and waves, and they go through every possible route at the same time, including two slits, including every part of a mirror. They're just weird. Matter is equally as weird. Everything is relative, but when you look at twins in spaceships, it kind of shouldn't be. And you have to do some acrobatical mathematics to try and justify to yourself why that is the case. Electrons can be everywhere at the same time until observed. Cats can be dead and alive. And time slows down, but nobody knows why. So that is the end. I will now stop recording, and if anyone's got any questions, fire away.